Hello again. After a short break, we will get here. Now we are heading to our main event right now. Mr. Fethi Ramazanoglu will be there right now. So he is graduating from the Koç University after he moved to USA and he took his master program from the MIT, which is the most brilliant university in the world. And after he moved to Princeton University, which is how can I say that? That's more than successful, right? Because it's Princeton. After that, he's coming back to Turkey and he's now in the one of the most successful universities in Turkey, Koç University right now. He's working as a associate professor. And he just joined us. He just attended our meeting. Welcome, valuable professor. Welcome.
Thanks for the invitation. Could you make me a co-host so that I can share?
I already host you, Professor. So if you want,
okay, cool.
You may start your presentation right now. Could you inform us what are you going to talking about in this presentation?
Sure. We can start with the. So this is the presentation. So the title is obvious. So theory and observation of black holes.
Okay, let's buckle up and listen to that. Thank you very much.
Okay, so if you think that you cannot follow something at some point, feel free to interrupt. That's okay if you spend time on answering questions rather than advancing through the slides. Okay, it's more important that you get something from the talk rather than completing the presentation, of course, within the time limits. So one of the reasons I chose this topic, this is related to what I do. I actually work on black holes myself in my own research. Not exactly in the, what I'm going to present today. This is not exactly my research area, but it's related to my research area. But this is actually the Nobel Prize from this year. The 2020 Nobel Prize in Physics was given to the theory and observation of black holes. And you'll actually see both of these figures in my talk. On the left, you actually see stars orbiting a black hole at the center that you actually cannot see. And on the right, this is actually a schematic explanation of what we call adaptive optics. It's a technique to see these stars. And I'll explain what those are. You don't need to know any of them, okay? So let's start with the Nobel Prize. So the Nobel Prize in Physics in 2020 is awarded 1/2 to Roger Penrose for the discovery that black hole formation is a robust prediction of the general theory of relativity. So in short, this guy, by the way, in this picture, he's the leftmost older person, Roger Penrose. He's a mathematician and a physicist, a very famous person. Okay, he did something about the theory of black holes. Okay, so what does it mean? For the discovery that black hole formation is a robust prediction of the general theory of relativity, you'll explain that. Okay, and the other half went to these other two people, okay, on the right-hand side of the picture, to Reinhard Genzel and Andrea Ghez for the discovery of a supermassive compact object at the center of our galaxy. So these two people actually did something about observing black holes. So one of the persons, the one on the left, Roger Penrose, did something about the theory. The other two did something about seeing what the theory said. Okay? And in the text, you see they discovered a supermassive compact object. What is a supermassive object? What is a supermassive compact object? We will also discuss those terms. Okay. At the center of our own galaxy, there is such an object. Okay. So let's start with the very basics. Okay, with the very basic concept of escape velocity. Okay, escape velocity is a very simple concept. So if I try to jump now, what will happen? I will actually rise up a little bit from Earth, and then I will come down, right? Because gravity actually pulls me back. If I jump actually faster in the beginning, I go higher, but I always come back. Okay, but if you have a rocket, or if you have Superman, and if Superman jumps, okay, Superman can actually just fly away and never come back. Okay, so there is a velocity that, so that if you live with that velocity from the surface of the Earth, you don't have to fall back to Earth. You can go to infinity. This is called escape velocity, the minimum velocity you should have, so that you can, if you just leave the Earth with that velocity from the surface and then do nothing, you don't do anything afterwards, then you can go to infinity. You don't fall back to Earth. This is called escape velocity. For Earth, this is something like 11 kilometers per second. A long time ago, in 1700s, a very smart British astronomer, James Mitchell, realized something. So if you look at the formula for escape velocity, G is a constant, universal constant, okay? High school students, some of you would know this, okay? The escape velocity is proportional to the mass and inversely proportional to the radius. So if you have a more massive object, it's harder to escape. Escape velocity is harder, is higher. If the radius is small as well, escape velocity also goes up. It's inversely proportional to r. So if an object is more, if you get Earth and make it smaller with the same mass, escape velocity would go up, because gravity is stronger in smaller distances and gravity is stronger with higher masses. So escape velocity depends on this ratio of m over r. So this smart guy, John Michel, realized that if the ratio of mass of an object to the radius of an object, m over r, is greater than this constant, c squared over 2g, where c is the speed of light that you learned about a little bit in the previous talk, and g is again the gravitational constant of Newton. This is a number. This is a constant of physics. You can calculate this thing. If mass over radius of an object is greater than this one, then the escape velocity actually becomes greater than the speed of light. What does that mean? That means even if you are light, you cannot actually leave the surface of this thing. You may try to leave, but you have to come back in the Newton's view. Okay. John Michel said that if there is an object which satisfies this m over r requirement, mass over radius requirement, then the light produced by this object, let's say you have a star like this, okay, because about third, let's say you have a star like this, which satisfies this m over r ratio greater than this number. Then basically the light this star produces never comes to you. So you learned how long it would take for the light from the center of the sun to come to us. So we are talking about surface of the sun to us. From surface of the sun to us, light takes about 8 minutes to come. But if sun has this much gravity, escape velocity will be greater than the speed of light. So even light won't be able to escape. So such a star would produce light, but you wouldn't be able to see its light. Okay, and John Michel called these stars black stars. Okay, this is kind of the precursor to the black hole idea. It's different from the idea of black holes. There are some very fundamental differences, but this was a very, very ingenious idea, to say the least. This is a Newtonian gravity. For black holes, you need general relativity. Okay, in 1915, Einstein discovered general relativity, and 1 year later, another famous physicist called Schwarzschild found a solution in general relativity which had a behavior like this. Oh, by the way, if you look at, so what kind of star this would be? Michel realized that if you have a star like sun, whose density is just like the sun's density, then you need the radius to be 500 times bigger. So you need a big, m over r. So you can get it two ways. Either you need a very big mass, or you need a very small r, okay? 1 over them, so that this ratio gets bigger. Okay. In general relativity, a similar things happen. There are fundamental differences. I won't be able to go into details. When Einstein came up with the theory of general relativity, Schwarzschild found a solution that actually something very similar happens. Okay. They realized that there is a solution to general relativity where you have a spherical object, perfectly spherical object. It has to be perfect. Okay. It's called a Schwarzschild black hole. Okay. And they realized that once you actually get close enough to this object, how close? If you get closer than this distance, r equals 2 times g over m over c squared, depending on the mass of the object, if you get to a certain distance of this object, there is no way of going back. Okay, so basically, if an object is compact enough, if its m over r ratio is small enough, so that you can get close enough to it. If you get this close, if you can get this close to an object without going inside it, by the way, this doesn't happen for the sun. So you should be still outside the object. They realize that once you enter this black region, then there is no chance of coming back. Actually, it's worse. Once you enter this black region, it's not that you can actually walk around or like just spend your life in this black region. No, once you enter this black region, you have to actually continue going to the center and then get part of the center. It means if you actually can have a star where you can actually put the whole star inside this black region. It's so compacted. Its M/R ratio is so that it's completely inside this region. Even the star itself cannot stay as it is, okay? Because nothing can stay as in a constant position in here. In Newton's theory is the problem, by the way. In Newton's theory, if you have a rocket, if you spend energy and force, you can actually escape. Escape velocity is only for an initial constant velocity and doing nothing later on. In Einstein's theory, once you go into this region, it doesn't matter how much energy you have, okay? Even if you have infinite energy, you actually have to continue collapsing to a point. So once an object becomes small enough, it means it has to continue to become smaller, 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 so that everything is concentrated right at the center, okay? Then you have this object called black hole. So a black hole usually is actually visualized by many people in popular science by this black sphere. Black hole is not the black sphere. Black hole is actually a point. All the mass of the object is at a single point at the center. This black sphere is the region from which you cannot escape. So the mass itself is actually, this is infinitely dense. All the mass is at a point if gravity is right, okay? And this is called a singularity because the density there goes to infinity, okay? But you don't have to see weirdness you don't have to go right on this red point to see the weird effects of a black hole. Once you are in this black region, then you start seeing the weird effect that there is no way of coming back. You have to actually continue going in. It doesn't matter how much rocket power you have. Okay? So the boundary of this region from which you cannot escape is called the event horizon. Okay, and the center where all the mass is and where all the matter is actually with infinite density in some sense is called the singularity. Okay, and Penrose is something very important to this singularity. Okay? So this was a pure solution, but for a long while people thought that this thing comes out of Einstein's theory. If you solve Einstein's equations, you actually get this solution. But people thought that this was just pure theory in the sense that, remember, to have such an object, you should first be able to actually squeeze enough mass into a small region. Remember, it's the ratio of m/r that matters to build this object. So either you should have a small mass and then squeeze it in a small region, or you should have a huge mass. But comparatively, always the radius should be small compared to the mass. In our universe, people thought there is no mechanism, there is nothing that could actually squeeze an object like this. We knew about the stars. When you look at the stars, actually, the ratios of, let's go to the previous slide. The ratio of m/r for the sun is much smaller than this. Its ratio of m/r for any star we knew back then was actually a lot smaller than this. But the thing is that theoretically, yeah, you can have such an object if you can squeeze a star much enough, but probably there isn't anything, any mechanism in the universe, any event in the universe that actually squeezes the matter of a star into a small region. Okay, that's about one down thing. Another important thing is that this object has to be perfectly symmetric. Okay, so people thought that this is important. So if you have perfect symmetry, perfectly spherical object, then you would have this. But once you don't have perfect symmetry, and in nature, nothing is perfectly symmetric. Every star has a little bump here and there. Once you don't have the perfect symmetry, then some people thought that you wouldn't get this. Okay, even if you try to squeeze material into a small region, it wouldn't actually collapse into a black hole. It would actually just get out. Okay, it would just bounce back, and then you wouldn't have anything weird like this black hole. Okay, so this view about black holes being only theoretical and probably not occurring in nature changed in the 1960s, both in terms of theory and in terms of experiment. Is there a question?
I'm sorry.
Is there a question?
Dear Professor, please continue. Some of our students got some issues in their home, I think so. You may continue.
I'm sorry, I have a question.
Sure, go ahead. You can ask questions.
So actually, my question was that if we reach the speed of light and like if we can survive to reach that speed, and then can we escape a black hole? And like, can we just pass it through?
So once inside this black region, no, even light cannot escape. Even light actually has to just continue going inside, and become part of the central region, which has infinite mass. Even light. If you are right on the surface, okay, right on the surface of this black region, then only light can escape. You and me, we can't escape because we can't go the speed of light. We have mass. Only light can escape barely from the surface. From outside the surface, in theory, you can escape. It would be hard, but you can. But very far away, it doesn't matter. If you are very far away from a black hole, its gravity is just like gravity of any other object, like Earth or the sun. Okay, so this weird effect only happens when you get close to the black hole. And again, it doesn't matter. Even if you are light, once you go into this black region, you are done. You will actually eventually fall into the center and become part of the black hole.
And the radius which we can actually how far we can be from this black hole in order to just pass it, and just for example, we should be in a, this is the R, right?
So, it's this formula. So if you put in the numbers,
like region to be from a black hole, right?
Yeah.
And my other question is that how is a black hole actually formed, and how is it just how does it exist if it's theoretically possible that we just squeeze a star so much that it just the radius will be like so little that a black hole...
That's what I'm going to explain next.
Okay.
So people thought that it wasn't possible. People thought that it wasn't possible because of these two reasons. Well, probably there isn't a mechanism to actually squeeze stars that much. And even if you try to squeeze them, if you don't do it perfectly symmetrically, then it would bounce back or something like that. And then you won't have a singularity. You won't have this infinite dense region and this black hole thing. Okay. And we later realized that both of these things are wrong. Black holes actually seems like they do exist. So this happened in the 60s. Okay, there were actually developments from, again, remember, general relativity came in 1915. For a long time, people thought black holes were just a theoretical idea that probably aren't out there in our universe. And in the 1960s, they realized an object called a pulsar. So a pulsar is a very special kind of star, which is extremely dense. Okay, so this M/R ratio, the escape velocity, for these are still not black holes. So the escape velocity from a pulsar isn't the speed of light, but it is actually close to the speed of light. It can be like 30% of the speed of light. So you have objects which are really, really compact. These are stars which are a lot more compact than whatever we had before. Normally, the average density of the sun, I mean, the density of these objects is billions of times bigger than the sun. How are these objects formed? If you have really a huge star at the end of their lifetime, they actually explode. It's another story. I don't have time to explain the details. Very, very massive stars explode at the end of their lifetime. It's called the supernova explosion. And then their central region, called the core, actually starts collapsing and becoming smaller and smaller and smaller. And after a while, they stop getting smaller if some conditions are realized. If the mass of the initial star is below a certain region, then this collapse of the star stops and you have a neutron star. And once people saw the neutron star, they said, okay, we have objects which are a lot more compact than we thought before. So it could be possible that maybe black holes also exist because, okay, let's say you start with a star whose mass is, I'm making up the number, 15 times the mass of the sun, and you end up with a black hole. What happens if you start with a star 100 times the mass of the sun? Maybe that one actually collapses so much that forms a black hole. Okay, so people realize that there might be possibilities. Okay, but still there was this idea about symmetry, right? If you don't have perfect spherical symmetry, you don't have a solution of Schwarzschild, which is not very hard, by the way. If you take a graduate level
YouTube channel kamu deh.
You
yang
know,
di
actually,
YouTube channel kamu, si Abil itu apa?
I assume this is not a question for me.
Abil nulis apa ya?
Dear Professor, please continue. Mrs. Ismeralde, please put off your microphone, please.
Yeah, it's hard to talk when I have to listen as well.
Yeah, sorry about that.
Yeah. So,
if you want
Penrose is the person.
Nulis, kamu bilang aja, what? Apa kek gitu. Kamu ini aja engage itu namanya nanti dinilai sama YouTube-nya engagement, kamu tuh menjawab nggak gitu.
Okay, I'm just, I'll try to continue, but it's in my ears. So
dear professor, can you, because of your hosting, could you click on it, the name of the Harry Esmeralda, and you can mute? Okay. She's unmuting yourself. You may continue. We are sorry for interruption.
Okay. Yeah, sorry for that. I tried to mute, but I can't actually mute.
Not necessary, professor. You may continue. You may continue your presentation.
Okay. So what Penrose did was actually, he explained that you don't actually need this perfect spherical symmetry idea. Okay, this was the idea. Again, here is actually the part of the proof he had. Okay, and if you read it, you don't understand anything unless you actually know graduate level mathematics. Actually, I don't even know the details of it. This is a very mathematical work. Penrose isn't just a physicist; he's a mathematician as well. A very good, very famous mathematician. He did many other famous things as well. Okay, and Hawking also contributed to this work. They came up with things called singularity theorems. They said that there is no symmetry needed. Once you actually put matter in a small enough region that M over R ratio becomes kind of small enough in some sense, it doesn't matter what kind of shape you have, if it's a sphere or some very weird shape. Once actually you can put enough mass into a small enough region, then you have to form a singularity. The whole thing actually collapses to a point if general relativity is true, and then you end up with a black hole. Okay, so theoretically as well, the obstacle in people's minds were lifted. Okay, so this was a big contribution of Penrose. And again, observationally, people had seen pulsars at the time, and they thought that probably black holes are out there as well. Now, theory part is kind of done, so we see that, okay, they can exist theoretically. Then how do we actually prove that they do exist? How do we observe black holes? And the problem with black holes is knowing without seeing. We just thought black holes are black. They don't just give out light. Okay, light cannot escape from them. That's how we see stars or pretty much any other object. So how can you see an object? Sorry, how can you know that an object exists if you cannot see it at all? Okay. At first, this sounds very puzzling, but if you are used to doing a little bit of physics, it's not really, because seeing is only one of the ways to know the existence of objects. Okay, there are other ways of knowing the existence of an object, and there are a few different ways of actually knowing that a black hole exists somewhere in the universe. And the way we will discuss for the most length, and the way this year's Nobel Prize was given to people, is actually related to what happens to objects nearby black holes. Okay, before this, actually go back to forget about black holes again, go back to the solar system. Okay, in 1600s, actually, even before Newton, Kepler, a very famous astronomer and physicist himself as well, realized actually that the motion of planets obey 3 laws called Kepler's laws. Okay, after Newton's equations, gravity equations, Newton's universal gravitation, we actually understand the reason for Kepler's laws. And basically, Kepler's law says that, let's say you have a central object, let's say you have Mars, okay, the planet Mars, and you have actually satellites of Mars, okay, moons of Mars going around it. Mars has 2 of them, natural satellites, Phobos and Deimos. Okay, there is a formula, if Newton's gravity formula is true, there is a formula that relates the mass of Mars to the orbit of Phobos. Let's say orbits of the moons of Mars. Okay, if r, now big R is not the radius of Mars. If big R is the distance from center of Mars to the orbit of Phobos, okay, orbit of the moon, and t is the time, is the period of the orbit. Period means how long does it take for this moon to make a full revolution. Okay, the mass of Mars can be calculated by this formula. Pi is a constant, G is a constant. Okay, you don't have to understand the formula, but the logic is that you can actually calculate the mass of a planet by only looking at the motion of a satellite going around the planet. Okay, if you know the distance from the center, if you know the radius of the orbit of the satellite, which is r, and if you know how long it takes for the satellite to make one revolution, that's t, the period, then from this you know r, you know t, these g is a constant that you know as well, you can actually calculate mass of Mars. This is actually how you calculate mass of Mars. Okay, this is pretty much how you calculate mass of any planet. You basically look at the orbits of the moons of planets, okay, natural satellites. You measure the distance of the orbits of the moons, you measure the periods of the moons, and then by the ratio, this formula, you can actually calculate. So from this formula, if you look at moons of Jupiter, you know actually the mass of Jupiter. If you look at moons of Mars, you know the mass of Mars. If you look at actually moons of Earth, moon of Earth, we have one natural moon, you can calculate the mass of Earth. This is, otherwise, how would you do it? There isn't a big enough scale in the universe, right, to weigh these things. And if you can do this for any object, if you can think of a planet like Earth as the moon of the sun, if you want, okay? The Earth is going around the sun, so using the distance between the sun and Earth's time for a full revolution around the sun, you can calculate the mass of the sun, okay? So any object who has moons around it, who has all other objects going around it, actually, for any object where there is another object going around, you can calculate its mass, okay? Then this gives you an idea. Actually, this immediately gave an idea. Remember that John Michell guy? I wrote the name incorrectly here. There isn't a final E, okay? Who actually came up with the idea of the black stars. If you have so much gravity in a star that light cannot leave. He actually realized a way. He realized that actually if there is no light, how would we ever know about these objects? Okay, and he realized that he could actually use this logic I just explained to you to actually know that there is a black star somewhere. So instead of a Mars, let's say instead of the solar system, remember I told you, you can calculate the mass of the sun using the orbit of Earth and the period of Earth. Okay, let's say you don't have sun, but you have a black hole at the center. You have a black hole and you have another object going around the black hole. Any other object which is not a black hole. Because this object is not a black hole, you can actually see it. So what would be the picture? So instead of this Mars picture at the center, you wouldn't see anything. There is no Mars. So you have emptiness. Around emptiness, you would see objects going in orbits, circular orbits or elliptical orbits. Okay. From the orbits, you would be able to say that, okay, if there is such an orbit, there has to be such a mass at the center. But when you look at the center, you wouldn't be able to see anything. Then you would say that, okay, there is a massive object where these things that I see are orbiting, okay? But this massive object itself isn't giving out any light. So it has to be a black hole, okay? So this is one of the ways to detect black holes. You don't see black holes itself, but you observe objects that are orbiting black holes. And from the orbits, you don't only know that there is a black hole, because if there is no central object, okay, if there is no gravity, an object just goes on a straight line. If an object is going on a circular or elliptical orbit, there has to be something at the center to make it go on a circle. Okay, and you know that there has to be a mass. You don't only know that there is a mass, actually, there is a formula to calculate how much mass there is at the center. Even if you don't see, okay, that object, you can calculate its mass, not only know its existence. And John Michell actually mentioned this. If you have another object going around this black star, you could actually, in principle, calculate its mass. Okay, so the idea is also very old. Okay, so to continue forward, let's talk a little bit about black holes. I won't be able to talk about many details of the black holes, but they basically come in two big varieties. Okay, one variety of black hole is called a stellar mass black hole, and it's in the name. A stellar mass black hole is a black hole whose mass is similar to the sun. By similar, I mean 5 times the mass of the sun, 10 times the mass of the sun, 100 times the mass of the sun. Okay, and these objects are actually formed from dying stars. The scenario I mentioned before, if you have a very, very massive star, a star which has a lot more mass than the sun, at the end of their lifetimes, these stars explode and their central regions actually start collapsing and they form a black hole. And these black holes come from stars, so their masses have to be similar to the masses of the stars. And then there is a second kind of black hole called a supermassive black hole. Okay? These black holes have a lot more mass. Their masses change from 100,000 times bigger than the sun to 10 billion times bigger than the sun. So these things actually have more mass than any other star. By the way, there is an upper limit for the mass of a star. A star cannot have, as far as we know, a mass of 1,000 times the mass of the sun. Okay, so these objects are a lot more massive than any star you can have. Okay, they are called supermassive black holes, and they are located at the center of galaxies. Okay, and if you remember this year's Nobel Prize, there is actually such a supermassive black hole at the center of our galaxy. The people. Two of the people who got Nobel Prize this year got their prize because they actually showed that there is such an object at the center of our galaxy. Okay, a supermassive black hole. It's not called a black hole yet. I will come to the next one. A supermassive compact object, they call it. Okay, so where does this thing, this idea comes from? Okay, the idea of supermassive black holes is also coming from 1950s. Actually, around the same time, the black hole idea was getting stronger. Even if actually a bit before that, people discovered object called quasars. Okay, you might have heard about this if you are into popular science. Okay, a quasar is basically a shortened version of quasi-stellar objects. So astronomers in early 20th century, in 1900s, okay, started seeing these objects which look like stars. They were points basically, okay, and they were giving lots of radio waves out. Normally a star gives out radio waves, but not this much radio waves. So these were very, very weird stars. Also, they realized that these quasars have an even weirder property. Their spectrum was completely strange. So what is the spectrum of a star? Again, I can't go into details. Because of quantum mechanics, actually, an element does not give out light at random wavelength. Okay, light has color, right? And color is actually related to the wavelength and frequency of the light. So an element actually doesn't give out light at any wavelength. Every element gives out light at certain wavelengths. Okay, hydrogen actually gives out light at, I don't know, at red, green, and then something, and then certain definite wavelength of green. And then sodium gives out light at another one. Neon gives out light at another color. Okay, this neon lighting, neon lights you have in the old times before LEDs. They are red because neon tends to give red light out. Okay, and you know exactly actually which element gives which kind of light. You can determine this from the experiments on Earth. This is actually how we know what sun is made of. You actually analyze the light from the sun and look at actually which wavelengths you have from it. You say, okay, oh, this is the wavelength from hydrogen, so you have hydrogen in the sun. This is the wavelength from helium, you have helium. You have sodium, you have this, you have that. And you can do this to other stars. When you do this spectrum thing, these quasars, it turned out that there were these lines, there were this light coming from these quasars, which didn't correspond to any element we know. Okay, and people were very surprised by this. I mean, are there some new elements out there? Is physics working differently in these quasars? Okay, and this looked weird to them. Okay, they soon realized that actually these weird wavelengths they see weren't new elements. They were actually seeing exactly the same light from the elements, but all the wavelengths, all the colors were shifted. All of them were shifted by a constant amount. Okay, why does this happen? We have to go into cosmology. I won't go into details, but because the universe is actually expanding, very far away objects are getting away from us. Okay, when they get away from us, there is something called a redshift. Okay, any light from an object which is very, very far away actually gets shifted. So all the light from that object actually gets shifted to the red. Okay, they look redder than blue. Actually looks like green. Green looks like red. Red you cannot even see because it becomes infrared if an object is very far away. Previously, people hadn't thought about it because they thought that quasars were actually like stars. Okay, because they look like points. And they were giving out lots of light. When they realized that these objects are actually shifting their spectrum, they realized that for so much change in the spectrum, these objects have to be billions of light years away. Okay, at the other end of the universe, these have to be. These aren't close by. Previously, they thought they were actually close in some galaxy, in our galaxy, Milky Way, or in some other galaxy. Then they realized these aren't close by, and these are very far away. Still, even though they are very far away, you could see them easily, which means they are giving out an enormous kind of energy, okay, an incredible kind of energy, because if something is very far away, it's harder to see them. And they could see these things kind of without that much problem. which meant that if you can see them from such a distance, their energy is incredible. And by incredible, I mean the energy of a single quasar is thousands times more than our whole galaxy. Okay, so there was this object which was thought to be a star. Now it's producing an energy which is actually more than a whole galaxy. Okay, a lot more than a whole galaxy. Okay, so how could such a thing happen? I mean, a star cannot do it. Okay? A huge galaxy cannot do this. They realized that they started speculating that when they looked at these objects in X-rays, they realized that probably the mechanism for this thing is something called an accretion disk. So if you have a very, very big black hole, by big, I mean a black hole with a very big mass at the center of a galaxy, eventually you end up some matter circulating this black hole, okay, in a gas. You have a disk of gas, a disk, okay, circulating around this black hole. And if you do some very advanced physics, you realize that as this gas actually starts falling into the black hole, it gets very, very hot and it starts shining, okay? And it starts giving out energy from the pole. So this is a black hole rotating, okay? So there is this material, gray material rotating around the black hole. As the material rotates and falls into the black hole, increasing the mass of the black hole, some energy is also pushed out from the poles. It's some very complicated mechanism I won't go into. And this energy that comes out of these axes, okay, is extremely intense. So whenever you see one of these beams, if Earth happens to be in the direction of these beams, you see these very, very energetic events, okay? So people started developing the theory of these. You know, there were many different people who came up with this idea piece by piece, and they had to actually look in X-rays to be able to measure these ideas. By the way, there are other Nobel Prizes in this. One of the X-ray astronomers who actually investigated this kind of mechanism, not for supermassive black holes, but for stellar mass black holes, also got the Nobel Prize in physics in 2002. Okay, so people realized that probably these things are actually, these things called quasars are just like this. They are actually these black holes at the center of galaxies, which are surrounded by this disk of material going around it. This disk isn't the galaxy itself, by the way. This is, again, a very small region of the galaxy. You have the stars, etc., in the galaxy. At the very center of the galaxy, you have the black hole and the disk of gas going around it, not a star, okay? Which gives out this enormous kind of energy, okay? So they had a theory for this as well, okay? So what happens at the center of our own Milky Way? This year's Nobel Prize was given for our own Milky Way, okay? The center of our own Milky Way is called Sagittarius A star. It's just the name of the center of our Milky Way, okay? And we don't see such a great, we don't have a quasar at the center of our Milky Way, okay? We don't have this incredible amount of power coming from it, but there is still a very strong radio source at the center of our Milky Way, Sagittarius A star, okay? So when you look in radio waves, so this thing is not actually a telescopic image. This, you take the radio waves and then you put radio waves into, so basically brighter regions in the second image means more radio waves, less bright regions means less radio waves. You see that there is this clear region, Sagittarius A, where you have lots of radio waves coming from us, okay? And people suspected that even though this is not a quasar, probably the reason for this much radio waves is also a supermassive black hole. Our own galaxy also is a supermassive black hole. It's not like a quasar. It doesn't have this huge accretion disk getting hotter and giving out this energy, okay? So it's milder, but it is there. But how can you make sure? How can you see actually such an object exists, okay? The problem is actually resolving this. So if you just try to see what's going on in this region, Sagittarius A star, okay, if you just look with a telescope, so this is our galaxy. This is roughly the size of the galaxy. So the size of Sagittarius A star is 60 million kilometers, okay? 60 million kilometers might look, oh, 60 million kilometers is a lot bigger than anything we have on Earth, and it's comparable to the distance from the sun to the Earth. Remember, distance from sun to Earth is 150 million kilometers. So it's, you know, 40% of it. So it's comparable to the size of the solar system. So this object is kind of big, if you want. It's kind of big, but the problem is it's also very far away, okay? The distance from the center of the galaxy to our own Earth, where we observe the Sagittarius A star, is 27,000 light years, okay? So even though this thing is not small, it's very, very far away. And because of it, its angular size is very small. So if you look at the angular size, of Sagittarius A star is called 10 micro arc seconds. What is a micro arc second? We will use it, so let me explain it, okay? So you know the degrees on the circle, right? A full circle is 360 degrees. So 1 degree is actually very small, okay? 1 arc minute is 1/60 of a degree, okay? So it's even smaller. 1 arc second is 1/60 of an arc minute. So it's even smaller. So 1 arc second is 1/3600 of a degree. Think of how small a degree is. 1/3600 of a degree is 1 arc second. Extremely small. A micro arc second is 1,000,000 times smaller than that. Okay. Basically, the size of the Sagittarius A star is 1,000,000,000 times smaller than a degree. It's extremely small, okay, in terms of angle. The problem is any observational device you have, any telescope you have, has something called the diffraction limit, okay? Depending on how big your telescope, like your eye, right? If 2 objects are very, very far away, if you have 2 points very close by, my 2 fingers, I can see them as 2 different objects. But if you actually if let's say you are in front of me and you show me your 2 fingers and I see you. If you go 100 meters away, I wouldn't be able to see your 2 fingers separately. That's called the resolution. If that actually the angle between the 2 fingers has to be big enough that I can see it with my eyes. The same thing is with the telescopes, actually. Nothing has infinite resolution. There is an ultimate limit that objects can see. And the best telescope on Earth, in theory, actually, has a resolution of 10 to the 4 micro arc seconds. What does it mean? It means if 2 objects are far away by 10 to the 4 micro arc seconds, this telescope can see them as 2 objects, otherwise it can see them, okay? It basically means it can see anything smaller than 10 to the 4 micro arc seconds. 1,000 micro arc seconds looks like a point to you. You can see its structure. And remember, the size of Sagittarius A star, angular size, is 10 micro arc seconds. So it's 1,000 times smaller than our observation limit, okay? It's called diffraction limit, okay? So our telescopes are 1,000 times worse than they should be to see this object. And this is not the biggest problem. Actually, the bigger problem is the atmosphere itself. Even if you have a perfect telescope, let's say you built a huge telescope. By the way, how well a telescope sees depends on how big it is in radius. Even if you build a huge telescope with a huge radius, okay, then, and let's say you have enough resolution for the angular size of the object, you wouldn't be able to see anything from Earth, right? Because of the atmosphere, okay? If there was no atmosphere on Earth, the light from any object would directly come to the telescope and you would be able to see it. But atmosphere isn't perfect. There is always wind, turbulence, okay? Things are moving. So even though light is coming in a perfect way, if say light is coming like this, okay, in perfect lines in some sense, this is called the wavefront. Because atmosphere is not homogeneous and it's moving and there is turbulence, light actually gets kind of blurred away, okay? So instead of seeing a point, if you look with even a perfect telescope, because there's atmosphere, you see objects move a little bit around. Okay? If you ever look with a telescope, if you're an amateur astronomer, you have seen this thing. Objects would move around, you would see a few copies of the objects, they would be lens, okay? And because of this, it doesn't matter how good a device you have, atmosphere actually gives you a resolution limit. Just because atmosphere gives you a blur, that is actually the ultimate limit. And that limit is basically 1 arc second, which is basically 100,000 times worse than what you can have. Which means with the atmosphere, there is no, even if you build a huge telescope, there is no hope of seeing this Sagittarius A star. So there is no hope of directly actually seeing if this thing is actually a black hole or not, okay? So how could these people get the Nobel Prize today, okay? They actually did 2 main things. First, they didn't actually use visible light that we see with our eyes. They used something called infrared light whose wavelength is actually more than the red light. Okay, why did they use infrared light? I forgot to mention this. This region around Sagittarius A star actually has a lot of dust in it. Don't think that space is completely empty. Space isn't empty. When you try to see the center of our galaxy, when you try to look with a telescope, there's a lot of gas around Sagittarius A star, which means light is actually dimmed by the dust. You can see into the dust. So it's a huge cloud of dust. it turns out visible light cannot pass through this gas, but infrared light can pass through this light. So you have to do infrared telescopy to actually see this thing. That's first thing. Even then, you have this resolution limit, right? Because of the atmosphere, actually, everything gets bad. And to overcome that, they use a technique called adaptive optics. They didn't invent this technique. The idea came in 1950s, and many different people contributed it, but they were actually people, the Nobel Prize winners were the people who actually combined everything. So what is adaptive optics? Adaptive optics, without going into too much, it does this. So remember, normally light is coming in this perfect shape line. Because of the atmosphere, it becomes like these wavy, weird shape. Okay? In adaptive optics, actually, you have a system which actually determines these deformation in the light. So instead of a perfect line, light front becomes these wavy shape. So you know the wavy shape. Okay, you first measure that wavy shape is, then you have a deformable mirror. What do I mean by that? You have a mirror whose surface actually can change shape in milliseconds. There are mirrors like that. These are miraculous things. Okay, so you measure how deformed light is, and you actually change the surface shape of the mirror so that it exactly matches these wiggles in the shape, so that after reflecting from a deformed mirror, it again becomes a straight line. So you have the perfect light, becomes wiggled by the atmosphere. Then you wiggle the surface of the mirror so that when the two wiggles cancel each other, after the mirror, you have the perfect light, so that you can actually eliminate the effect of the atmosphere. This is called adaptive optics. You know, go look at Wikipedia more for it. Go look at the internet. It's an incredible technique. And with this, actually, you can only see. You know, you can have enough resolution. So using this, they actually haven't been able to go down to. So what do you need for Sagittarius A star itself? You need 10 microseconds. They haven't gone down to 10 microseconds, but they're kind of 10 times worse than that. But they weren't actually trying to see Sagittarius A star directly. What they were trying to see was stars orbiting Sagittarius A star. Remember, you cannot see Sagittarius A star, the black hole itself, because there is no light directly coming for the black hole. What was the idea to observe the black hole? You look at other objects orbiting the black hole, and from those orbits, you can actually calculate the mass of the black hole. Okay, and that's what they did. Okay, so they actually looked at stars which were orbiting the central region. So this origin here, that very small black dot there, is Sagittarius A star. And all these colored ellipses here are different stars orbiting the central region. Okay, so the most important one is this red one. Okay, it's called S2. Okay, because it's the one with the closest orbit to the Sagittarius A star. Okay, but all of them give you information. So by looking at these orbits, by observing, and these orbits actually, they take time. You have to observe these things for years and years. By looking at this orbit, they actually measured the kind of the radius of this orbit. In ellipse, you don't have to measure the radius, but they measured how big this ellipse is. They measured how long it takes for the star to make a full revolution. And from that, they could actually calculate the mass of the object at the center. So this closest star is still about 1,000 times further away from the event horizon. This distance that you cannot escape from. So these stars are orbiting, so they aren't actually inside the black hole. They are orbiting the black hole. So they are 1,000 times far away from that orbit, but still that's a good number. I mean, previously we couldn't even get close to this one. Okay, so when you look at the orbit and calculate the mass of the object at the center, so you have all these stars going on here. At the center, you don't see anything. So what kind of object should be at the center so that you can explain the orbits of all these stars? When they put in the numbers, okay, they realize that in a region of a parsec, basically, so their resolution limit, in a region of about 1 light year cube, they had a mass of 10 to the 15 times mass of the sun. So I like to skip this thing. After some calculation, they realized that the mass of the object at the center is 4 times 10 to the 6, basically 4 million times the mass of the sun. Okay, so there is an object which is in a very small region, and it has 4 million times the mass of the sun. I mean, there are other possibilities. You might think maybe there are, some millions of stars there in a very small region, and they actually ruled out all those possibilities. It can't be that this thing is this region with 4 million times the mass of the sun cannot be a collection of many stars. It has to be basically a single object. Because of this, they call it a supermassive object. They don't still say definite because we still have more tests to do. So they call it a compact object. This is a very small region with very high mass, which is called a compact object. They don't directly call it a supermassive black hole, but pretty much everyone believes that it is actually a supermassive black hole. As our resolution in telescopes gets better and better, we will actually be more and more sure that it is actually a supermassive black hole. Okay. So where do supermassive black holes come from? It's not exactly known. I mean, again, they are very different from the stars, you know. I mean, normal black holes, stellar mass black holes, I should say that normal. Stellar mass black holes, as I said, they are basically dead stars. We know where they come from. Where do you get these objects with millions or billions times the mass of the sun? It's not exactly known how they grow, okay? People think that they start small in the beginning with some core, with some baby big black hole at the center of the galaxy. Eventually, it starts actually gathering material from around and gets bigger and bigger and bigger, accumulates matter. And sometimes actually even galaxies merge. In case you didn't know, galaxies in the universe also actually collide with each other from time to time. And when two galaxies collide, the black holes at the supermassive black holes at their center, they also become one. They also go around each other and then merge to become one bigger black hole. So these are all actually factors contributing to it. So the original black hole at the center of a galaxy, merging of galaxies, accumulating, you know, matter from the galaxy itself, etc. But we don't know for sure how much role all these mechanisms play. Hopefully, we will know better with more observations, though. Okay, so I told about this year's Nobel Prize, but actually there are other ways to observe supermassive black holes. You might have heard this if you are into popular science. Last year, very big news was the first photograph of a black hole. You might have seen this photograph here. Okay, so these people actually used what I can call an extreme version of interferometry. As I said, every telescope has a certain resolution limit. Okay, if you want to see directly near the horizon of a black hole, you need extreme resolution, and we don't have it. This year's Nobel Prize winners actually don't have it. They observe the stars around the black hole, which are 1,000 times kind of far away from the black hole's event horizon. What happens if you want to see the event horizon? The people came up with this idea called event horizon telescope. Okay? Again, I can't go into details. There is this process, there is this physical phenomenon called interferometry, interference, okay, which basically says that if you have two telescopes very far away, okay, if you can somehow actually use them together in parallel in communication, then effectively you actually can have a resolution of a telescope whose radius is the distance between two telescopes. A telescope here or in Turkey, let's say a telescope in Brazil, if you can connect these two telescopes together in a specific way, then the angular resolution you get, okay, the resolution you get from this telescope can be as well as the telescope whose radius is the distance between Brazil and Turkey. Okay, and they did this with not two telescopes, I don't know, with like 10 or something telescopes all around the world. Basically, they connected different telescopes together, and then effectively they had a telescope whose size was the size of Earth. Then you could barely see the black hole of not our own galaxy, by the way. This photograph was not the black hole of our own galaxy, but a nearby galaxy, okay? When they actually looked at it, because that black hole was bigger and easier to see, so that they could take this photograph. And they want to take more photographs, like they want to look at our own galaxy, Sagittarius A star, using the same technique as well, but they have to modify certain things. Okay, so this is another technique coming on. Before this thing, actually, all the photographs of black holes you saw were just imaginations. This is kind of more realistic. Okay, let me be faster because I used up too much time. There's another way, actually, of seeing supermassive black holes called gravitational waves. So it turns out if you have two objects in space going around each other, Einstein's general relativity predicts that these two objects actually shake the space-time in some sense. What does it mean to shake space-time? It's weird to explain. I mean, space is empty, so how can you shake something empty? In Einstein's general relativity, space isn't really just empty. It's not that it's filled in something, but space-time actually has a structure. It has curvature. So when two objects go around each other, they actually change the structure of space-time, which can be measured. These are called gravitational waves. Okay, and these actually were measured 5 years ago for the first time for two stellar mass black holes. If you have two kind of smaller black holes going around each other, we can measure them with our current instruments. And people who did this actually got the Nobel Prize in 2017. Look it up. Now there is a project to do this for supermassive black holes. When galaxies merge and you have two supermassive black holes going around each other, again, detect how these supermassive black holes going around each other, getting closer and then becoming one. Can we actually see this thing? And people are actually planning to see it with an instrument in space. They are going to send satellites into space to actually measure these little shaking of empty space, if you like. It's called laser interferometer space antenna, LISA. It's funded everything. It's going very well. It will be actually sent into space in about 2030. It was 34, but project is going well, so it might be earlier. We don't know. With this, actually, we will be able to know a lot more about supermassive black holes. We'll be able to know about how many of them there are, their evolution in time. As cosmology went on, as universe actually got older, how did the galaxies merge, etc. We will actually know more about this. Let me cut here. I only took a lot of time, and have questions. If you have questions, are more important than me talking more. Thank you.
Thank you very much, dear professor. Can you make me host again, please? Because we have to move to the answer session. You can click on me with the right click and just click on the make host.
So what's your username here?
INTOC.
INTOC.
INTOC,
Okay.
yes.
You could make me a co-host, by the way. It's easier.
Yeah, apparently it's not working. We tried that. There is something.
Ah, okay.
Okay, thank you very much. If you want, you can close your presentation because we will move to the question and answer session. We got plenty of questions to ask you. We just got via WhatsApp. So may I start to ask?
Sure, go ahead.
Thank you very much. For first question is coming from the Bahar. Black hole, can the black holes gate off the other universes?
No, these are very. So you are. Am I still sharing my screen or?
Yeah, you are still sharing, but it's not problem. It's not problem.
Okay, so no. Okay, there are these speculative ideas that there are these things called white holes, which are opposite of black holes, in the sense that you cannot escape from a black hole once you go into this black region, right? White holes have this white region you cannot get into if you want to. They cannot repel you. This is a completely theoretical idea, and people think that they don't exist in our universe at all. So there was this very speculative idea that you actually, if you can go into if you go into a black hole, you can come out a white hole on the other side, or you can. There are these things called wormholes, which connects one part of space-time to the other. Most people think that. I mean, again, theoretically, you can have. But with black holes, you cannot have them. Okay, so we don't know exactly what happens at the center of the black hole. The singularity theorem says that if you assume general relativity, then there has to be this infinite density thing at the center. But the problem with that is that actually disagrees with quantum mechanics. Which one is correct? The problem is we don't have a theory that combines quantum mechanics and Einstein's general relativity, which is called the quantum gravity theory. We don't have such a theory, and you need such a theory to know exactly what happens at this singularity. So we don't know exactly, but still, even though we don't know, no one believes that actually if you go into a black hole, you come out somewhere else. If you actually even approach most of the black holes, depending on the kind of the black hole, you will, because of the tidal effect, you will be actually you'll get elongated. Look up the word spaghettification. So becoming like spaghetti. Okay? Because look up the words. Basically, if you get close, even before you go into the event horizon, you go into the black region, actually you start getting bigger, longer and longer and longer and longer. So you'll be ripped apart and killed. Depends on the black hole. In the supermassive black hole, this won't happen. Depends on how small the black hole is. If you go in, probably you will just fall in some time and then crashed into the center and just become a part of the black hole. You won't come out anywhere. Okay, there are very, very speculative ideas out there about coming out. They aren't really serious.
then can we say the Hollywood lied us again?
Which one? Interstellar, you mean?
Yeah.
Not really. Interstellar is a great movie, actually. The science advisor for Interstellar is a Nobel Prize winner. He's one of the guys who got the Nobel Prize in 2017. One of the guys, actually. So most of Interstellar is very accurate, but not all of it. The very ending isn't, yes. So we don't know. I mean, this movie, right? There is some creative license, so you don't have to be exactly physical. A lot of the things in that movie are actually accurate, technically. Then comes the speculation part. So you can do it for fun, but if you are asking me as a scientist, what's the reality? Again, I put an asterisk there. I say, we don't know for sure because we don't know what's really happening near the singularity, because we don't have this theory for it yet. But we think that Einstein's theory cannot be correct because it doesn't agree with quantum mechanics there. Okay, so maybe it happens, but there is no reason to believe that you come out another way. And there are many reasons to believe that you just get crashed and die if you fall into a black hole.
Okay, so may I ask a question, because I just wonder that. But it
Just go ahead.
If it's ridiculous, don't mad at me, please, Professor, because I am very ignorant about that.
There is no
I'm
such
just a
thing.
basic English teacher, so I want to ask it. If I trapped into a black hole, what will I see? Or can I see the out inside of the black hole? If it's possible to trapped in the black hole, of course.
Remember what I told you about black hole. If you go in, so again, by the black hole, there is a singularity at the center, which is a point. That black region is just empty space. It's just the part of space you cannot enter. So I assume you're asking what happens if I go to that black region from which you cannot escape. Things from outside can come into actually inside. That's fine. The thing is that once you go inside, you can't even stay still. You have to actually continue getting closer to the center. You just continue going closer to the center. Okay, so that you will get crushed. There is this idea that right before you actually enter the event horizon, that boundary of the black region, there is this idea of seeing an infinite time of kind of thing. There is such a thing. There is this, as you learned in one of the previous talks, time doesn't flow the same way, right? Depending on the observer. And this is true for someone who's close to the edge of the event horizon and who is outside, very far away from the event horizon. So time flows differently. And that aspect of Interstellar is actually very accurate. Time flows differently for different people. Okay? Once you go inside the black hole, actually, it doesn't matter what happens. In a very short time, you will just continue. And again, even if you have lots of energy, you cannot even stay still. You have to continue going in to the center and then just get crashed. You won't be seeing anything. You won't be seeing anything from regions closer to you, to the center. You might be able to see some things that are coming from outside, though.
Okay. The recent, I'm moving the other question. The recent photograph of a black hole, is it real or not, or it's just a making by the artificial intelligence? If I see a black holes like that, I will see exact a black hole.
Okay. A very good question. I mean, but the question is a false dichotomy in the sense that you say, is it a real photograph or is it something created by artificial intelligence? I mean, why would something created by artificial intelligence be not real? Let me explain how this thing is based. So this is not what you have in mind with the photograph. This is not, you turn a telescope and then you turn a camera and then you just click and then that is what would be in the camera. No, yeah. This image here isn't obtained that way. If you mean real, by real, if you mean that, this image isn't gotten that way. This image is gotten, you basically collect lots of data, a lot of data, okay? So remember I mentioned to get this image, you have to connect telescopes which are on opposite ends of the world. One telescope in Hawaii, one telescope in the South Pole, one telescope in Europe, okay? This connection isn't done in real time. Basically, you collect some data in one telescope, the other telescope, and then you combine all this data and then see, okay, what does this data tell me about what these telescopes are seeing? And you do lots of actually algorithms on this data. And then you have to do some guesswork as well in the end. It's some, not guesswork, but you have to do some modeling. You have to assume some things. Okay, what should this photograph look like so that I can have it? So yes, this thing isn't just a photograph taken by a camera, not a photograph like that, but we think it's an accurate photograph. So if you were close enough to the black hole, this is a very good representation of what you would see. People who actually did this, they are trying to actually they're trying to con you into something. They're trying to cheat. Actually, they had a few separate teams to get this image, because there is this part of the process where you have to actually assume certain things about what the shape would look like. Otherwise, you cannot actually get the shape from the data. You have to assume something. You could fool yourself, right, into getting a nice shape. Because of this, they had separate teams which didn't communicate with each other, and they all actually came up with their own final, photographs, if you want, final shapes, final images. And then they compared if different teams got, similar images, or they completely got different things, so that actually we are just deluding ourselves into seeing something. And they saw that they got pretty much the same image. I mean, not exactly the same, because there is some noise in the data, but all the different teams, got the same image. So we are pretty confident that this is a good image. But it's a good question in the sense that this is not like just taking an image with a photograph. Okay, there is lots of data processing. Terabytes of data actually were processed to get, not terabytes, sorry, petabytes of data was processed to get this image.
There will be 2 more questions, and we will end. I know you're a very busy person, so I will not keep you a very long time. So next question is there anyone or anytime will be able to create a tiny black hole in a laboratory? Or if it's possible, how does it take to make one? How long does it take to make one?
I mean, again, a very general question. I mean, will it be possible in the future? I mean, there isn't something that prevents, that says that it's impossible. With our current technology, it's impossible. There was a scare like 10 years ago when FHC opened, when a particle collider opened. They said when particles collide in this detector, they might form small black holes, which might become bigger, and then it will be the end of the world or something. Okay, there was pretty much no probability that would happen with our current technology. If you have extremely high energies, you can do that. But we don't have such a technology on Earth. We can't even foresee such a technology in the future. Okay, so in the foreseeable future, no, we won't be able to produce black holes ourselves. But there is this unforeseeable future. Like 200 years ago, people actually wouldn't be able to imagine iPhone. But we have iPhone now. So in that sense, who knows? It's not theoretically impossible, but technically, it seems impossible in the foreseeable future.
Thank you. It's the last question. Mrs. Pasupati say, dear professor, I have always fascinated by the supermassive black holes. Have the ability to show up to the nearby matter. My question is, how do black holes produce their enormous jets of hot and fast matter?
Yeah, okay. This is a very, first, we don't know for sure. I mean, we know some of the details. Remember, I mentioned, I explained how these quasars actually produce their energy. They basically have these disks of material going around. It's not the disk actually. You see, from the axis of the black hole, kind of perpendicular to the disk, there's this huge beam of energy coming out. These are called jets. There are different ideas about it. One of the leading ideas is something called the Blandford-Znayak mechanism. Okay, and these are very technical things. It's basically about the magnetic, it's about the interaction of magnetic fields, the plasma that is rotating around the black hole, and how the plasma actually behaves as it's trying to fall onto the black hole. As it tries to fall on the black hole, it can't fall on the black hole, and then some of the energy actually escapes from the poles, if you want, from the axis. Okay, that's the rough idea, but exactly we still don't know. Actually, this is an active research area. We are trying to actually simulate these things, try to understand them better, but simulating these things are extremely hard. Okay, we are getting better and better. We know some of the basic components of magnetic fields are an important part of it. Particle creation out of vacuum is a part of it. Plasmas are a part of it. Rotating black holes are a part of it, but I didn't mention that. These black holes have to be rotating, actually, so that you can have this kind of mechanisms. But again, the details, you have to be an expert, and even experts still don't understand some of the finer points. Again, Wikipedia in general, people sometimes go very bad on Wikipedia. Oh, it's not like a peer-reviewed source. Wikipedia tends to have very good introductory information about these things. I would say go read the Wikipedia article about quasars and jets, and then follow the links there. That's a very good place if you are really interested in reading. And there is a YouTube channel. Some of you might know this. PBS Spacetime. PBS is Public Broadcasting Corporation. PBS Spacetime. They are a great popular science channel about astronomy, astrophysics, gravity, cosmology, things like that. So go watch their videos. I mean, they are far better than any other popular science source I have seen. I regularly follow them. I'm a Patreon contributor to them. So I actually do advertising for them everywhere. So PBS Spacetime, go watch it.
I just noted. Dear participant, we will share this channel with you after the meeting in the our WhatsApp group. So can we say we are still on the crawling era of discovery of these black holes as a humanity?
We are still in what era? Sorry?
Crawling era.
Oh yeah. Of course. I mean, again, theoretical idea was very far. As I said, before this image came out, and again, it was a very good question. This image isn't just a photograph. It's like kind of lots of data processing and a little bit of guesswork together. Everything we had was just someone drawing something based on our ideas. There wasn't really data of what happens near the black hole. By the way, this is not the black hole itself. So what is this image, by the way? At the center, the black region is the black region of the event horizon, a bit bigger than that actually. It's something bigger called the shadow of the black hole, whatever. And this is the gas around the black hole, basically giving out radio waves. Okay, so this came out before last year. In terms of observation, actually, we haven't done very much. Okay, and this idea of sending something into space to measure the gravitational waves from black holes, actually, that was also very important. Why did these people who measured gravitational waves got the Nobel Prize? Once, it was an extremely hard measurement. Two, we now actually have a way of seeing this. Black holes, they don't produce any light, but when two of the black holes go around each other and then merge to become one black hole, they actually shake space-time. You can detect these shaking of space-time. So you can't actually see black holes, but you can kind of hear them in some sense, this shaking, okay? And this is actually a very powerful tool to actually directly observe black holes. So actually, it's very accurate to say that we are just crawling to understand black holes, but things are actually going on very, very fast. I mean, the first black hole merger we saw with gravitational waves was 5 years ago. Today, we have something over 60 different events like that seen. In the near future, we will have thousands of events like this seen. Event Horizon Telescope, we will have a few more images like this. Unfortunately, we won't have many more images. This technique only works for kind of nearby galaxies, nearby supermassive black holes. So we will see a few of them. And the Nobel Prize, they are increasing their accuracy. So they will observe more and more stars, closer probably. And then they will actually know more about the object at the center of our own galaxy as well. So in terms of observation, we had lots of theory. Now we have observation. And one thing I forgot to mention, all these assumes Einstein's general relativity. As we observe more, maybe we will see. Remember, Einstein's general relativity came in 1915. Before that, people believed that gravity was actually governed by Newton's universal theory of gravitation. And Einstein said that, okay, that's approximately true, not exactly. You have to change these little parts in Newton's theory. Maybe Einstein's theory also needs changing. Okay, so by observing these black holes, maybe we will find something that doesn't agree with what Einstein says, and then we will have an even better theory of gravity. That's actually something I personally work on. I'm trying to see if these observations can lead to something that says that Einstein's gravity actually doesn't explain certain things. So you need another theory. Okay, so we are really crawling. It's always crawling. That's the fun of it, right? If it was all done, you would just read it from a book and learn it. Now you can actually work on it and discover it yourself.
Professor, we are really appreciate. Really, thank you very much. Thank you very much. We are really glad to see you in here. Thank you for attend our meeting and show you way of to the black holes. And I don't know how can I thank you personally. You answered our questions about that issue. Thank you very much again. It was the 4th meeting of the INTOC, and we will continue the next week. Thank you very much again, ladies and gentlemen. Mr. Ramazanoglu, Fethi Ramazanoglu from the Koç University showed us a really marvelous lesson in last 1 hour. Thank you very much, Mr. Ramazanoglu again.
Thank you for listening.
Our pleasures.
Sorry. Can I ask a question? I'm sorry, because I asked in chats and I think you didn't see it.
I mean, I have time. I can answer one more question. I don't know if other people have time. I don't know your schedule. I don't want to mess up your schedule.
So can I ask it?
Mrs. Karime,
Moderator.
Mr. Ramazanoglu, dear professor, if you got time, just one more question, last question.
Okay.
Okay,
Okay.
Mrs. Karime, please ask away.
Okay. So about the question that was asked about if we get into a black hole, what will happen to us? Actually, you said that we'll go through and we just go and get closer to the center. But I was thinking, why wouldn't we just explode? Because like the gravity of a black hole would be so much, and like the pressure on our body would be so much. So why wouldn't we just explode it?
Yeah,
Like,
that's what I said. There is this spaghettification process. It's not explosion, actually. You will be torn apart. So it depends on the black hole. If you actually try to approach a stellar mass black hole, not the supermassive black hole, actually even before coming to the event horizon, okay, gravity won't crush you. What will happen is that, let's say you are going head on into a black hole, okay, with your head first and then feet behind, okay. So there will be gravity on your head and gravity on your feet, and that gravity will be slightly different because it depends on distance. And the difference actually try to make you longer and longer and longer and longer, and then if you have fun. That's called spaghettification, because any object will actually become long, 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 like a spaghetti. So this happens, though this thing depends on how strongly this happens, depends on the mass of the black hole. Interestingly, this happens if the mass of the black hole is small. If you have a supermassive black hole, actually this won't happen. You can just go in, if you have a rocket ship, you can go into the event horizon without getting ripped apart. Fine, you will be fine outside the event horizon. Inside the event horizon, you will be also fine for a while. You will just continue, but after a while, as you get close to the center, then yeah, spaghettification will happen. You will first be torn apart, but eventually all those parts kind of torn apart, they will all join the center, the singularity in the end. That's the ultimate fate. If you go head on, of course. I'm assuming you aren't on an orbit or something.
right.
Okay.
Thank
Anyway,
you so much.
thanks again for listening.
Thank you very much, Professor. Thank you very much. So,
Excuse me. Can I also ask a question? I'm so sorry.
Mrs. Jasmine, I'm sorry about it because we have to close it down. We are really late after the program. We are sorry, but if you send us the question via WhatsApp, we will send us our professor, and we will get you back the answer via WhatsApp. Don't worry about it. Thank you very much.
Okay, so I don't have your WhatsApp like number. Can you give it to me?
If you write your phone number, we can add you. Don't worry about it. So before closing down,
Okay.
28th November, we will continue our 5th meeting, global meeting with the INTOC, global brainstorm. We will continue next week. Thank you very much for participating. Thank you very much. See you later.
Bye.
Bye.